seems as though this program keeps locking up, so what I'll do is I'll do this in 10-minute segments until I get to the end. I think that it will hold 10 minutes worth of material. So we're now looking at experimental probability. Experimental probability is what happens when you conduct an experiment, not what happens if you live in a vacuum or what is supposed to happen. It is what actually is the outcome of your experiment. And so what we're going to do is we're going to toss 2 coins 500 times, and we're going to record the results. So what happens is, at the end of the 500 tosses, heads occurred 137 times, heads tails occurred 115 times, so on and so forth. Experimental probability is the number of times that it occurs within the experiment over the number of times that you perform the experiment. So if we let E be the event of getting a head on the first coin, find the experimental probability of E. A head on the first coin would be this one or this one. So we would add those together. 137 plus 115, 252, back up there, there we go, 252 out of 500. So the experimental probability of E, and we would write that as P of E, is equal to 252 over 500. So let me fix the color there. 252 out of 500. Alright, in the next one, you have 200 people who are given a taste test, so we're going to do the experiment 200 times. So when we're looking at experimental probability, that's going to be our denominator. They're given a test taste of 2 different types of crackers. 148 of them preferred cracker A, 41 of them preferred cracker B, and 11 have no preference. Find the experimental probability of a randomly selected person preferring cracker B. Well, cracker B, 41 people in the experiment chose cracker B out of 200, and that's our experimental probability. Theoretical probability is if we lived in a perfect world, this is what should happen. So what we do is we write out our sample space, and we've talked about how to write out a sample space. You count how many of the outcomes are in your event, put that number over the number of items that are in your sample space. So we're tossing 2 fair coins, and we're going to find the theoretical probability of each outcome in the space. So our sample space, 2 coins, we have heads, 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 tails, tails, heads, and tails, tails. And I'm going to go back and clean that up a little bit. Little lines. Alright, so the theoretical probability of each outcome in the space. Heads, heads occurs 1 time out of 4. Heads, tails 1 time out of 4. Tails, heads 1 time out of 4. So each outcome in that sample space has a theoretical probability of 1/4. The event of getting a head on the first coin. So the probability of getting a head on the first coin, we have 2 that are heads on the first coin, and there are 4 outcomes in our sample space. the event of getting at least 1. So that means 1 or 2. So getting 1 or 2 heads. So that's 1, 2, 3 out of 4. So that would be 3/4. Okay. So example 7. Again, I point you back to your book. Don't seem to have my book handy. So, rolling 2 fair dice. I pointed you to that chart earlier, and it has all the possibilities. So find the theoretical probability of A, and A is getting 7 dots. Well, you could get 1 and 6, you could get 2 and 5, 3 and 4, 4 and 3. You could get 5 and 2, or 6 and 1. That's 6 out of, and there were 36 in that sample space. Probability of getting 8 dots. Well, 2 and 6, 3 and 5, 4 and 4, 5 and 3, 6 and 1. 6 and 2, excuse me. So that's 5 out of 36. The number of ways, or the number of outcomes in your sample space that fit the event over the total number of items in the sample space. So getting at least 4 dots. At least 4 dots means 4 dots, 5 dots, 6 dots, 7 dots, 8 dots, all the way up to 12 dots. An easier way may be to count how many ways do you get 1, 2, or 3 dots, and then subtracting it from the 36. That would be quicker. So there's no way to get 1 dot. To get 2, there's only 1 way. That's a 1, 1. To get 3, there are 2 ways. You could get 1 and 2 or 2 and 1. So there are 3 possible ways. So 36 minus 3 is 33 out of 36. So if you went the other way and you counted all of those, then you would still get 33 over 36. I just went the opposite direction and subtracted those that were not included. Alright, so we have a jar that contains 4 marbles. 1 is red, 1 is green, 1 is yellow, and 1 is white. And we want to draw 2 marbles without replacing the first one, and we want to find the probability of each. So we could have sample space, red, and it's without replacement, so red green, red yellow, red white. We could start with a green, green red, green yellow, green white, or you could start by pulling a yellow, yellow red, yellow green, yellow white, or we could start by pulling the white first. White red, white green, white yellow. Did good there to the end, and then that little line showed up again. So white, yellow. Alright, so event A, we want to find the probability that one of the marbles is red. So we count 1, 2, 3, 4, 5, 6. So the probability of event A is 6 over, and there's 3, 6, 9, 12 events in the sample space, or outcomes in the sample space. The first marble is red or yellow. So again, the probability of B is also 6 over 12. The marbles are the same color. Well, that's not possible because we did not replace the marbles. So the probability of C is 0, or 0 over 12, which is still 0. Event D, the first marble is not white, so we want everything except for white, which would be the probability of D is 9/12. The probability that neither marble is blue. Well, that's the case on all of these, so it's 12 over 12, or 1. And this is where I'm going to cut this section.